Hey friends, welcome. Today we are going to discuss one of the topic of irreversible thermodynamics or non-equilibrium thermodynamics, that is Onsager relationships. Now, this Onsager relationships we have already seen in the first lecture that we have discussed. Today, using a very simple reversible reaction, we will investigate this Onsager reciprocal relationships kinetically and thermodynamically. So for first we will examine the reaction kinetically, and then we will discuss the concept thermodynamically, and for that we will consider a simple reaction wherein we are considering that A is converting into B, and suppose if we consider that K1 is the rate constant for the forward reaction and K minus 1 is the rate constant for the reversible reaction or the reverse reaction, then the rate, that is the rate of consumption of A, that is dCA upon dt, we can write it as K1CA minus K minus 1 CB, and similarly the rate of formation of B also will be given by the same expression, that is K1CA minus K minus 1 CA, as the reaction is a reversible one. Now, when the system is under the equilibrium condition, then we know that whenever a system is under equilibrium, the rate of forward reaction is equal to the rate of reverse reaction, and for a macroscopic reaction or generally in irreversible thermodynamics, we are considering that our system is divided into large number of very small systems, and this system is under its own equilibrium. That is the concept of local equilibrium that we have already seen. Okay, so for the macroscopic rate, or suppose if we can write that JCH is the macroscopic rate, and then that JCS, as the system is under equilibrium, this JCH is the rate, and that will be equal to minus dCA upon dt, and that will be equal to dCB upon dt, and that will be equal to 0, because when the system is under equilibrium condition, at that time the net rate is always same, and that we can write it equal to 0. Now when the rate is equal to 0, then under that situation this term we can write equal to 0, and hence both these terms can be equated, and hence we can write K minus 1, we can write K1 CEA is equal to K minus 1 CEA. EB. So over here the superscript E, it indicates or it refers to the equilibrium condition, and when we rearrange this expression, we can write K1 upon K minus 1, that will be equal to CBE upon CAE, and K1 upon K minus 1 we can write it equal to K, which is the equilibrium constant or another equilibrium constant which refers this ratio. Okay, now suppose if we consider that alpha is the extent, then alpha A at any particular time we may write it as CA minus CEA, and similarly alpha B we can write it as CB minus CEB. Okay, now suppose if we consider that X moles of A, it reacts to give B when equilibrium is attained, that is under equilibrium condition, we are considering that X moles of A has reacted to give X moles of B under equilibrium condition or when equilibrium is attained, then the concentration, that is CAE and CEB, both are the concentrations at equilibrium. So the concentrations over here, that is, we may write CEA, we can write it as Ca minus X, as X is the moles of A consumed when the equilibrium is attained. So the concentration of A under equilibrium can be written as the concentration of A minus X will give us the concentration of A at equilibrium. And similarly, CEB, we can write it as CB plus X, because at under equilibrium condition or when equilibrium is reached, X moles of B is formed and this will add to the concentration. So we can add both these expressions, and when we will add both these expressions, we will have CEA plus CEB, that will be equal to Ca minus X plus CB plus X. So both these terms will be cancelled out and we will be left with Ca plus Cb. So hence the total concentration at equilibrium will be equal to the concentration at any time t. So what we can again do over here is that we can add both these terms also. So when we add both these terms, that is alpha, so we will have alpha A plus alpha B, and that will be equal to, we have Ca minus CAE plus CB minus CEB. So over here we will have Ca plus CB, and then we can take minus common and we will have CAE plus CEB. So both these terms will be cancelled out and we are left with 0, because this is equal to again same. So this will be equal to Ca plus Cb, and this will be cancelled out and this will be equal to 0, and hence we can write that alpha A is equal to minus alpha B. Now we have already written that JCH is the rate of the reaction, and this JCH is equal to this or this. So over here we can substitute, or JCH is equal to, we can write this particular expression, and CA, we can rearrange this particular expression and write the expression of CA, that is CA will be equal to alpha A plus CEA and CB will be equal to alpha B plus CEB. So both these expressions we will be using now. So we will have JCH is equal to K1 into CEA plus alpha A minus K minus 1 into CEB plus alpha B. Okay, and we have already seen that alpha A is equal to minus alpha B. So over here in place of alpha B we can substitute alpha A, and also we have seen that K1 alpha EA is equal to K minus alpha EB. So both are same. So when we simplify this expression, we will have K1 CAE plus K1 alpha minus K minus 1 CEB minus and this minus, so alpha B we can substitute minus A, so this will become plus K minus 1 alpha. So both these terms will be cancelled out as both are same, that is K1 CEA is equal to K minus CEB. So that can be cancelled out and hence we are left with, and hence we can take alpha A common from both the terms. So we will have alpha A into K1 plus K minus 1, and again we can take alpha A K1 common, so we will have K1 into 1 plus K1 upon K. So this K1 upon K minus 1 upon K, and we have K1 upon K minus 1 is equal to K, so this will be 1 upon K. So our expression will become alpha A into K1 into 1 plus 1 upon K. Okay, so this is the expression of our rate when we are looking at our system kinetically. Okay, moving on to the thermodynamic aspect of this particular reaction, and thermodynamically we will consider the affinity, where we have already seen that affinity of a particular chemical reaction, and in previous lecture also we have seen that affinity for this particular reaction we can write A is equal to mu A minus mu B, where mu is the chemical potential. So over here A is our force. Okay, A is our force, and the flux, that is the rate we have written is it as JCH. So JCH is the rate. So this rate is equal to the flux, and the affinity of the chemical reaction, it is the force. And according to the Onsager's relationship, we know that flux is directly proportional to the force, and they are related by a proportionality constant. So over here also we can write JCH is proportional to the flux A, and then this JCH is equal to LA, where L is the proportionality constant, and we are going to find out the expression, or what will be the value of this proportionality constant. Our expression will become JCH is equal to L into mu A minus mu B. Okay, and mu over here is the chemical potential of the system. Okay, so chemical potential, we know that chemical potential for a particular system at constant temperature and pressure, that is mu I, it is given as mu I 0 plus RT ln Ci or RT ln Xi, where Ci is the concentration and mu I 0 is the chemical potential in its standard state. Okay, so over here for the concentration of A and B, we have written that alpha A was equal to Ca minus CeA. So this we can rearrange to get Ca is equal to alpha A plus CeA, and again we can take CeA common, CeA into 1 plus alpha A upon Ca. So this will be our concentration of A, and similarly we can have the concentration of B. So our chemical potential, that is mu A, will be equal to mu 0 A plus RT ln CeA plus RT ln 1 plus alpha A upon CeA. Clear? I have separated both the terms, and similarly for mu B, we will have mu 0 of B, that is plus RT ln CeB plus RT ln 1 plus alpha B upon CB. This will be the expression. Now we have A, that is affinity, is equal to mu A minus mu B. So we have the value of mu A, we have the value of mu B. So both this can be substituted over here. So we will have mu 0 of A plus RT ln CeA plus RT ln 1 plus alpha A upon CeA minus, we will have mu 0 of B. We can take both these terms in the square bracket, plus we can write RT ln CeB minus, we will have RT ln 1 plus alpha B upon CeB. Okay, now over here the first two terms in both this expression, it refers as the equilibrium chemical potential of A and equilibrium chemical potential of B. And when the system is under equilibrium, the equilibrium chemical potential of A is always equal to the chemical potential of the constituent B, and hence both these terms in our square bracket will be cancelled out, and hence our value of affinity A will be, we can take RT common from both the terms, So we will have RT ln 1 plus alpha A upon CEA minus ln of 1 plus alpha B upon CEB. Okay. Further, as the value of alpha I upon CIE it is very less than 1, the expression that is ln 1 plus alpha A upon CEA, or we can write alpha A over here, so no need to generalize it. So this we can write it as almost equivalent to alpha A upon CEA. Okay, because as this is very less than 1, okay, then obviously the value of ln will be almost similar to the value which we get by dividing it. Okay, so hence over here we can substitute this over here. So we will have A is equal to RT alpha A upon CEA minus alpha B upon CEB, and that is equal to, and over here we know that alpha A, we have already seen that alpha A is equal to minus of alpha B. So over here in place of alpha B we can substitute minus of alpha B, we can substitute alpha A, and we can take alpha A common out. So we are left with RT alpha A into 1 upon CEA plus 1 upon CEB. Okay, now further we can divide and multiply this expression by CEA and CEA. Okay, so over here when we will be multiplying CEA in this expression, so we are left with RT alpha A upon CEA into, this will become 1, and this will be CEA upon CEB. Okay, and we have seen that earlier that K was equal to CEB upon CEA. So over here in place of this term we can replace it by K. So we are left with RT upon alpha A CEA, that will be into 1 plus 1 upon K. So we have, so this we can substitute now over here in this expression, and hence our rate, that is JCH, is equal to L into A, and that will be equal to L into RT alpha A upon CEA into 1 plus 1 upon K. Okay, and so this is the expression of rate thermodynamically, and when we compare or when we looking at both these expressions, then this expression we can equate or we can write it equal to, this is the expression which we got kinetically, so we can write it equal to alpha A into K1 into 1 plus 1 upon K. Okay, so when we simplify this expression, so both these terms and alpha A will be cancelled out, and we are left with L RT upon CEA, that is equal to K1, and we can rearrange this expression in the term of L. So we will have L is equal to K1 into CEA upon RT, and this K1 into CEA, it is nothing but we can write it as mu EF, that is the rate of forward reaction under equilibrium condition. So over here we can write it as mu EF upon RT. Okay, so over here this is our final expression, and this is the value of L, or the proportionality constant that we are getting. And over here we can see that this, the phenomenological coefficient L, it depends on the equilibrium concentration of A at a given temperature. So as we know that RT and K are the constant, so the phenomenological concentration is proportional to, or it is dependent on the equilibrium concentration of our product or of our reactant which we are taking. Okay, so thus this verifies our Onsager's relationship or Onsager's linear relationship. Hope the topic is clear. Thank you very much.